All right, so in this video, I'm going to talk briefly about the relationship between current and voltage with regards to the capacitor. This is fairly important when it comes, especially when it comes to your labs, because you're going to need to see and observe kind of what's going on with your capacitors when you're building your circuits here. So let's begin here. So if I just have just a very simple sample circuit like you see here with a couple of meters attached to it to try to observe what's going on, you can already imagine it could be something you do in lab or so. We know that the capacitor is modeled by this equation here. So capacitance equals to your charge divided your voltage. Now, in this unique situation, I have actually an alternating current here. So it is somewhat time dependent or time varying. So what I see here so essentially what we have here is it's essentially Q of T over V of T instead. All right, so if we go ahead and isolate our equation so that your charge is on one side and then your capacitance on and the voltage on the other side, we can go and actually take the derivative of both sides, knowing that current is actually dq dt, and we're going to use that to our advantage here. So once we take the derivative of both sides, what we're left with is your current is equal to your capacitance times dv over dt. Now, if you relate this to the equation for a line here, y equals mx plus b, and let's just assume to set b equal to 0, like so, what we're left with is y equals mx. So this relationship that we see here is actually a fairly linear relationship, and that's represented in this graph right here. So I have current on the y-axis, and then I have dv dt on the x-axis. And then when I plot this, it's actually a straight line. And the slope, I know it's a little messy here. So if I zoom in just a little bit, the slope is actually I over dv over dt, which is equal to the capacitance like so. So the relationship we can assume is that, well, as your capacitance goes up, the change in voltage with respect to time is going to drop as well. Right, and then what about for voltage here? So we're going to go ahead and solve for voltage. So we're going to go back to this equation that we ended up with the current, and we're going to go ahead and actually integrate both sides of the equation. Well, what we're going to do first is we're going to make sure we have dv on one side. So do the math to move dv onto one side. We're going to integrate both sides for t naught to t final here. And when we set v naught is equal to 0, essentially we end up with this equation here. Voltage is equal to 1 over capacitance times the integral from your starting time to your final time times I dot dt, like so. So that's how you mathematically model the relationships between current and voltage with a capacitor.